Well, hello everybody. Today we are finding the distance between parallel lines. In an earlier video, we found that distance graphically. We graphed the lines and then using the perpendicular slope, the opposite reciprocal slope, we mapped out the distance between them. We found the segment, we found the point of intersection, and then we used both the Pythagorean theorem and the distance formula to find the length of that segment. So that was finding the distance between them graphically. Now I'm going to show you how to do it algebraically. This method doesn't require a graph at all, but again, I'm going to use the graph so the visuals will reinforce what's going on and help me show more clearly and hopefully help you to understand a little better. But again, this method could be done completely without looking at a graph at all. Just to make our lives easier, I'm going to go ahead and use the same equations that I used in the other video. So I'm going to go ahead and start by typing the equations of those parallel lines in. The first one was 2x plus 7. Oops, let's go ahead and get it there. 2x plus 7. And our second equation is 2x minus 3, which of course results in two parallel lines, one with a y-intercept of -3 and one with a y-intercept of 7. And again, our goal is to find the distance between them. Now again, the distance between two parallel lines is the shortest distance between them, which can be found by finding the length of the perpendicular segment. And there's infinitely many perpendicular segments between these two lines. So we can actually make it anywhere we want to. So just as in the previous video, we're going to pick an easy value. We're going to use the y-intercept, which is going to prove very helpful when we go to write the equation of the line, because we'll already know what b is. So I'm going to go ahead here, and I'm going to make a point on the y-intercept right there at 0, -3. So let's go ahead and fill in some information here. The slopes of these two lines, as we know from the equation, the slopes are 2. And we know the y-intercept. We already know what the equations are, but I'm going to go ahead and write them down just to reinforce visually what they are. So this red line was y equals, it has a slope of 2 and a y-intercept of -3. And this blue line has a slope of 2 and a y-intercept of 7. So y equals 2x plus 7 and y equals 2x minus 3. Now what we want to generate is the equation of a line that is perpendicular to both these lines. And as I mentioned, we are going to go ahead and use this y-intercept right here. So our perpendicular line is going to pass right through this point. So I'm going to label this as b, and I'm going to call b -3. Now we have to recall slopes of lines that are perpendicular are opposite and reciprocals. Unless, of course, you have the vertical and horizontal, and then there's 0 and undefined. So I'm going to write the perpendicular slope as perpendicular m, and then I'm going to do the opposite reciprocal. Now, the slope of this is 2. Here, I'll do it right here. And 2 is 2 over 1. You flip that over, find the reciprocal, and you get 1/2. But it needs not just to be the reciprocal, it needs to be the opposite reciprocal. So I'm going to put those two things together, and I'm going to come up with the equation of my perpendicular line. So y equals mx plus b, so y equals -1/2 x minus 3. Now again, we could do all of this without a graph, but I just kind of would like to reinforce what it is that's going on here. So I'm going to go ahead and just show you visually that line right there has a y-intercept of -3 and a slope of -1/2, which would take us right through there. So there is our perpendicular line. And of course, the point we're going to be looking for is that point right there, Because if you're going to find the distance between two lines, you need 2 points, right? This is the distance we're going to be looking for. So that's the point we're trying to find. Of course, we know what that point is. It's -4, -1. And what we actually just did was we actually just solved the system of equations. We just did it graphically. But the whole point of this exercise is to show you how to do it algebraically. So I'm going to come up over here and I'm going to write our system down. What are we looking for? We're looking for the intersection of this purple line and this blue line. We already know the intersection of the purple line and the red line. It is at -3, or rather as an ordered pair, 0, -3. But this is the one we're looking for algebraically. So if I write down that blue equation, which is y equals 2x plus 7, and I write the equation of the perpendicular, which we made purple, y equals -1/2 x minus 3, we want to find what? What are we looking for? We're looking for when that y and that y have the same value. Because in most places, that blue line and that purple line, the y values are completely different when the x values are the same. But right there, when the x values are the same, the y values are the same. When x is -4, y is -1. So we can solve, again, we solve graphically. The other two methods we could use are substitution or elimination. This is set up perfectly for substitution because they both say y equals. So what am I going to do? I'm going to take this value for y, this expression, 2x plus 7, and I'm going to put it right there for that y. And so what do I get? I get 2x plus 7 equals the value that we have here, which is -1/2 x minus 3. I want to know when the y value on the blue line and the y value on the purple line are the same for the same value of x. And this equation is going to give me that. Now, I don't necessarily like that -1/2. We can solve it with the fraction. But as many of you know, if you want to eliminate a fraction, you can multiply by the least common denominator, which in this case is 2. So if I double this entire equation, multiply everything by 2, it becomes 4x plus 14 equals -1/2 times 2 is going to be -1, or just the opposite of x, minus 6. Now, I haven't changed any of the solutions. By doubling all of the equations, since I doubled everything, the solution will remain the same. The x solution to this equation, the x solution to this equation will be the same. Then I'm going to go ahead and add x to both sides. And that's going to give me 5x plus 14 equals -6. And then if I go ahead and subtract 14, I can finish up this equation with 5x is equal to -20. Dividing by 5, I get x equals -4, which just happens to be what we got right there. Now, if we didn't know that y was -1 from the graph, we could then take that -4, and we actually will, and plug it into either one of these equations. And it doesn't matter which equation we use because we have the same value of y for the same value of x because we're finding the solution. So if I use that first equation, y equals 2x plus 7, and if I insert the value we found for x, 2 times -4 plus 7. Well, 2 times -4 is -8, and -8 plus 7 is equal to -1. So we get y equals -1. So now we know we have confirmed this point. So even if we didn't have the graph, we would know we have the point -4, -1. That is the point of intersection of my perpendicular line, my purple perpendicular with the blue line. And then we have this point over here, my y-intercept, which is 0, -3. That is the point of intersection of my purple line with my purple perpendicular with my red parallel line. And so what do I need to do now? I need to find the distance between those 2 points, and that will be the distance between the lines. And of course, to find this distance, we can, if we wanted to, we could go to the graph and draw a right triangle and use the Pythagorean theorem, but that would kind of defeat the purpose of our algebraic theme here. So we really should use the distance formula. So again, the distance formula, d is equal to the square root of x2 minus x1 squared, the difference of the horizontal distance of the points, the x values, the difference of those, plus the difference in the y values, or the vertical distance squared. And again, the distance formula is just the square root of the Pythagorean theorem, square root of a squared plus b squared. So again, you can call x2 and x1, either one of these could be. So I'm going to go ahead and call this point x1 and y1, and this one's going to be my x2 and y2, although they are completely interchangeable. So if I went ahead and did this, so x2 minus x1 is going to be 0 minus a negative 4. But subtracting a negative is the same as adding a positive, and I'm going to end up with 4 squared. So again, that's the difference between the x's. That is my horizontal distance, which would be 1, 2, 3, 4 going across. And then I'm going to have my vertical distance, which we're going to find out in just a minute, is 2. My y2 minus my y1 is going to be negative 3 minus negative 1. But subtracting a negative, same as adding a positive. 3 negatives plus 1 positive gives me 2 negatives. 4 squared, last time I checked, was still 16. Negative 2 squared is 4, and we get the square root of 20. So the distance here is the square root of 20. And as we discussed in the other video, the square root of 20, many times we like to simplify that. So the square root of 20 can be written as the square root of 4 times 5, which is the same as the square root of 4 times the square root of 5, which is 2 root 5. So it's the square root of 20, or 2 root 5. That is the exact answer, which of course is the best answer. If you need an approximation, we could go ahead and make and measure a segment from there to there. That's where we ended up at negative 4 and negative 1. And it will go ahead and tell us that approximate distance, which is 4.47. So if you want the approximate distance, you could say it is approximately 4.47 units. And again, we did all this on the graph, but as you can see, there's a ton of algebra on the screen, and it all could have been done without the graph at all. Well, I hope you helped. I hope I helped you understand how to find the distance between two parallel lines algebraically.